Distinguished member of the audience, I'm Claudio Urrea, research full professor from the Electrical Engineering Department at the University of Santiago of Chile. It's my privilege to expound before you the extensive technical intricacies underpinning this comprehensive research focused on modeling, analysis, design, and sophisticated control technique for an innovative four-arm Delta robot architecture geared toward ultra-high precision trajectory tracking tailored for automatic food preparations applications in demanding industrial scenarios. The overview of this presentation includes the context and motivation of the work, the proposed topology of the four-arm Delta robot, the mathematical model of said robot, the control strategies designed and implemented, simulation test cases, the result of the closed-loop simulation, the conclusions obtained, possible future work, and finally, the references used are presented. Regarding the context and motivation of this work, today Delta platforms are valued for their fast movement but have mathematically complex nonlinear kinematics. Advanced control strategies are vital for adequate multi-axial trajectory tracking capability. Fuzzy logic is adept at handling uncertainty and high nonlinear dynamics, and interval type 2 fuzzy is more resilient to unpredictable disturbances. Therefore, the objective encompasses meticulously designing, modeling, and rigorously validating pioneering fuzzy control methodology on a novel four-arm Delta manipulator, where submillimetric accuracy and repeatability are imperative for the automated preparation, handling, and packaging for perishable foods. The proposed four-arm Delta robot topology considers four equivalent kinematic chains with actuated rotational joints, strategic 90-degree square arrangement, conferring 3 uncoupled translational degrees of freedom, and lightweight 1 kilogram payload capacity. Then, using rigid body dynamics and optimization tools, we derive comprehensive static and dynamic models encompassing nonlinear kinematic formulation, providing both forward and inverse solutions, and an analytical dynamic model obtained via the virtual work principle. Extensive modeling of the robot provides an accuracy mechatronic representation and serves as a basis for designing control strategies and conducting extensive testing under strict real-world conditions. For this, they were considered direct and inverse kinematic solutions, dynamic representation through the virtual work principle, determination of the workspace. The incorporated phenomena are viscous and Coulomb friction, delay control, structural vibrations, and joint compliance. Through more than 100 simulations, tracking performance was evaluated in 4 representative trajectories under conditions that reflect implementation constraints, such as control signal saturation, time delays up to microseconds, friction compliance and damping effects. For this, they were considered smooth quantic polynomial trajectories, conventional PID controller fine-tuned by pole placement, fuzzy PD and PID controllers with optimized non-symmetric rules, interval type 2 PID for uncertainty management. To develop simulation test cases, the following were considered: 4 representative trajectories, strict real-world conditions such as actuator speed and torque limits, delays of up to microseconds, frictions, compliance and damping, and external disturbance rejection tests. Additionally, using comprehensive performance indices, we carry out an exhaustive quantitative evaluation with the metrics integral square error, integral absolute error, and integral square error. The result of the closed-loop simulation showed the following. The interval type 2 PID was the one that provided the best overall performance. All fuzzy approaches far outperformed the PID controller. Excellent sub-millimeter tracking accuracy demonstrated, and disturbance rejection was achieved 30% faster. Therefore, the proposed modeling, design, and controller of the 4-arm Delta Parallel Manipulator were conclusively validated, rigorously demonstrating unprecedented precision capabilities. This particular work allowed the design, analysis, and control of a novel 4-arm Delta Parallel Manipulator oriented to precision applications in the food industry. From a rigorous geometric model, forward and inverse kinematic analysis of the robot were developed. In addition, its inverse dynamic was analytically obtained by incorporating valuable realistic aspects that are usually omitted. Cutting-edge control strategies based on Type 1 and interval Type 2 fuzzy logic were implemented and compared. The fuzzy controllers demonstrate significantly superior performance compared to the conventional PID controller in the analyzed metrics. The interval type 2 fuzzy logic controller with PID action demonstrates the best trajectory tracking capability and disturbance rejection, validating the potential of this advanced technique for complex and highly nonlinear manipulators such as the one studied. In summary, this study made contribution in analytical modeling, intelligent control, and comparative analysis of cutting-edge strategies, establishing solid foundation for industrial applications of high-precision data parallel manipulators. Although technological advances have increased the reliability of robots, they are not exempt from failures. The literature presents limited research on fault tolerance in parallel manipulators. Therefore, future work will address issues such as degradation in the presence of faults and reconfiguration of control laws. Furthermore, the incorporation of realistic elements such as saturators, delays, and dynamic effects in joint add greater realism to the analysis and laid the foundation for a reliable digital twin of the robot, fostering future work on physical implementation. Finally, the references used are shown. Thank you very much for your attention.